All right. Welcome everybody to ME773 Project 3, the highly anticipated sequel to ME773 Project 1 and 2. I'm Jack Pockbeer. Let's get started. So for part 0, let's get to know your classmate Jack, that's me, better. So I like all 4 of these characters from various TV shows. Which one of these characters do you think is my favorite? This is very subjective, but I'll give you 3 seconds. Okay, if you said letter A, you would be correct. His name is Guts. He's from a Japanese manga called Berserk. He's very cool. So let's get started. So for part 1 of this project, it asked for us to determine the ranges of average emissivity for the ground, plastic, and the sky. And the reason we need to do this is because we're going to be looking at a hoop house, greenhouse setup. So we're going to need to know things like such as the ground emissivity, the hoop house emissivity, which would be like made of a plastic, and then the sky as well. So for the ground, dark wet soil to light dry soil, you could have an emissivity of 0.98 down to 0.90, where the dark wet soil would have a higher emissivity compared to the light dry soil. Before I go on, let me actually tell you what emissivity is first. So what emissivity is it's the ratio of the radiation emitted by a surface to the radiation emitted by a black body at the same temperature. This emissivity may assume different values based on whether one is interested in emission at a given wavelength or direction. So here in this little picture I took from the book, it has that emissivity at a certain wavelength, and direction is a function of wavelength, direction, and temperature. And you can see that it's the ratio of radiation emitted by a surface to the radiation emitted by a black body, where the black body is independent. It's a perfect emitter and absorber, and it is not a function of direction. So knowing this, we can talk about these emissivity values a little bit better. So for plastic, I looked up at the hoop house example that Dr. Derby gave to us, and I found out what the plastic they're using is. So it's just a polyethylene. And I found that polyethylene's emissivity is 0.94 or range from 0.92 to 0.98. And then for the sky, at a night clear sky, I found it to have an emissivity of 0.74 or 0.73 plus a little bit more times the dew point temperature. So what are some more things that affect the emissivity? As we looked at, soil depends on the moisture content and the composition. The plastics can depend on their composition again, the surface finish, and even the color. So when looking up some of these values, I found that different colored plastics would have different emissivities. I think if it's white or if it's black, it would have different emissivity because of that. For the sky, it depends on atmospheric conditions, cloud cover, and humidity can affect the emissivity values. Also for surfaces not listed here, like metals and some conductors, metal emissivity can change based on the shininess kind of it. So if you have an oxide forming, like rust on metal, or I can't remember what it's called on copper, like the Statue of Liberty, that will affect the emissivity. And also temperature can affect the emissivity for conductors. But for practical purposes, dark wet soil and some plastics may be able to be treated as a black body. Also, the sky can be treated as a black body as well due to its area being so large. So the heat rate transmitted to it can be assumed as a black body, but its emissivity is still not 1. Next slide. So for part 2, it asked for a sky temperature of -40 and a ground temperature of 0.5, calculate the heat transfer rate without a hoop house. So the ground will be directly emitting to the open sky. So I set up a resistance network to better picture this problem. I don't think it was required, but also I'm not going to be assuming the ground is a a black body. I'm going to use the emissivity value that I found. So here are some of the values we'll need to know. It's given that the hoop house radius is, or the hoop house area, I can calculate as 222 meters. I have both my temperatures, the emissivity of the ground, and then the view factor, which I'll talk about in the next slide. So setting up this resistance network to find out, these with the emissivities will act as a resistance where the Q here can act as kind of a current going through the resistance analogy. So you can see the ground here and the radiation being emitted from the ground is going out in all directions to the air. So solving for this, or you have your driving potential on top over the resistance to get the current or the heat transfer rate, you get about 32 kilowatts without the hoop house in place. And these results can actually change based on cloud cover. If clouds were in the way or were interfering, that there were a layer between the ground and the atmosphere, this would act as a further resistance, and this would result in decreased heat transfer rates to the sky. So as I mentioned in the previous slide, I had a view factor in there that was 1. Here's how view factors can be calculated. So calculating view factors. What a view factor is the fraction of the radiation leaving a surface I that is intercepted by another surface J. So for us, now let's consider the hoop house. So we have a hoop house over our ground, and the hoop house will be a hemispherical cylinder. So one tactic to find this view factor is reciprocity. Also, you can just use to find a view factor, what's the word I'm looking for? Observation. Your observation, you can see if it is either 0 or 1. So looking at this problem, you can see that all of the emission or radiation coming from the ground is going to hit the hoop house. So this ratio, the fraction of radiation leaving the ground to that is intercepted by surface J would be the same. So it would be 1. The ground does not see itself at all. Knowing this, we know the areas as well. We could then calculate the view factor for F2 to 1, or the hoop house to the ground. So we found that this is 0.637. That makes sense. Not all the radiation being emitted from the hoop house is going to hit the ground. It could come off of an angle here and then hit itself, the hoop house. So it wouldn't be 1. Now, we can also try to find the view factors for the outside of the hoop house to the sky and the sky to the hoop house. So that'd be F2 to 3 that I've labeled and F3 to 2. So again, we can use reciprocity to aid in this. Also, from observation, I am going to assume that F2 to 3 is 1. I don't know if this is a perfectly reasonable assumption, as some of the radiation from the hoop house could be going down, which would be going into the outside ground. But I'll be assuming that it's 1. Also, once we solve for this, we'll get this ratio of the areas where we have A2 over A3, and A3 being the sky compared to a small hoop house, relatively small hoop house, A3 is infinitely larger. So looking at this, this would make F3 to 2, the view factor from 3 to 2, go to 0, since the area of the sky would be so large in comparison to the hoop house. So for part 4, we can use all the information that we've gathered so far to now implement and try to solve for the heat transfer rate from the ground to the sky, now with the hoop house in place. So we're going to set up another radiation network, assuming the hoop house is opaque. As you can see here, we have the black body emissive power and the radiosity. So we set up our resistances again, going through each material, and then you could actually add a couple more, but these other 2 resistances that you could add on the end would all have A3, the area of the sky, in the denominator, so they would just go to 0. Solving for this, where we'd have the top being our driving potential from the Stefan-Boltzmann law, and the resistances on the bottom, we can solve for the heat transfer rate from Q1 to 3, which should be from the ground all the way to the sky, going through the hoop house, which is my surface 2. Another thing you could do is solve for T2, because we don't know that parameter yet. To do this, since the current or the heat transfer rate through this series circuit is the same at any point, we could also look at the black body emissive power at this point, which would be for the hoop house itself, and solve using the resistances between the ground and the hoop house material itself. So doing that, we would have this solve for T2 would give us this temperature right here. So now that we have those equations, we can vary the emissivity from 0.01 to 0.95 to see how that affects the heat transfer rate, and also to see how this changes T2. To do this, we'll write a little bit of, copy these equations into E's, and then create a couple parametric tables so that we can vary it from 0.01 to 0.95. So with this radiation, or with the hoop house acting as a kind of radiation shield, we can see that the heat transfer rates are significantly lower than without, like the previous case where we just looked at the ground straight to the sky. So in this right graph here, the heat transfer rate, as the emissivity increases to 0.95, we can see that the heat transfer rate also increases. However, it only gets up to about 19.5 kilowatts, which compared to earlier at 32 kilowatts, which is significantly less. Then on the left graph, you can see that as we increase the emissivity, we can find that the temperature of the greenhouse, or the hoop house itself, increases. So that will have effects when looking at the plants actually living in there, which I'll talk about. So to explain some of this is that the radiative heat transfer between two surfaces is directly proportional to the difference in their temperatures and the emissivity of the surfaces, with the Stefan-Boltzmann constant in there as well. So Q equals sigma, or the emissivity times Stefan-Boltzmann constant, the temperature difference, each temperature to the fourth, the difference of those times an area. So if we have a higher emissivity, that means more efficient radiation exchange, leading to a larger heat transfer between the two surfaces that you're looking at being emitted. And we can see that as the emissivity increases, so does the heat transfer rates. So for the last part, we want to see how this would affect the plants in there, and also some things that weren't considered. So, excuse me. We saw that as we increased our emissivity and added the hoop house, we got larger and larger temperatures. And going back, the emissivity of the polyethylene was very high, 0.94. So that's intentional, so they can get large temperatures to keep the heat inside of the hoop house. So this will lead to a longer growing season for the crops. You can grow farther as temperatures go colder outside. You can grow for longer, and then as temperatures start to warm back up, you can start planting and growing crops earlier than without the hoop house. Some things not considered in this analysis could be the humidity. The humidity itself with water vapor in the air could affect some of the radiation. It would absorb some of the radiation and act probably as a buffer. Also, we didn't consider any convection effects. The airspeed inside the greenhouse was not accounted for. This could be non-trivial. This would affect the heat transfer rates as well. And then also what could affect our results is differences in vegetation cover. So we were just considering a flat ground or dirt. However, if you were to have a bunch of really thick plants in there, that would also act as a barrier to heat transfer. So I had also thought of this, used an AI image generator to get a very cold cactus in a coat. And I thought that was kind of fun. So last slide, here's some of the references that I looked at for some of the heat transfer or the emissivities, and then the book being the last reference. So thank you for listening and following along, and subscribe, like, hit that bell, and get ready for Project 4 coming soon.